Thank you. I'm going to talk about MRI quality control for radiation therapy planning in general, and in particular, some of our primary product offerings in this area, the MagFan RT and S162 Phantoms, and the associated fully automated analysis platform, SMARI. There's rapidly growing application of MRI to radiation therapy planning due to the superior soft tissue contrast and the wide variety of contrast mechanisms. There are several challenges to deal with, most notably dealing with geometric distortion, which in many situations can actually exceed a centimeter or more. There's also a scarcity of effective and simple quality control methods, and further complicating the situation is the general complexity and all the pitfalls associated with MRI. The quality control needs of radiation therapists are actually quite a bit more rigorous than those of diagnostic radiologists. Furthermore, the scanners that are used in radiation therapy are often used well outside of the departments where MRI has traditionally been located and where the experts reside. So what is needed from an MR quality control protocol suitable for radiation therapy planning? First, it must be efficient to perform. It must be easy to interpret by non-MRI specialists with deeper information available for those with specialized knowledge. It should be thorough, providing 3D measurements wherever possible, and sensitive to many types of scanner failures, including those that are of elevated importance in radiation therapy planning. It should also be sensitive to errors in machine configuration and sequence setup. The Phantom Laboratory offers multiple products in this space. In this presentation, we're going to focus on the two flagship MR products, the MagFan RT and S162 Phantoms. Though perfectly suitable for diagnostic imaging, these phantoms were designed to meet the particular needs that arise in radiation therapy planning. The MagFan RT is the larger of the two phantoms and is designed to cover regions suitable for torso imaging. The smaller S162 is designed to fit in modern-day head coils. Both phantoms give a thorough checkup of the scanner and are supported by a fully automated analysis platform available through a web-based interface. There are two major challenges in supporting large field of view distortion measurements: managing the weight of the phantom, which could easily be too heavy to be moved by one or even two people, and making a phantom that performs many different tests on an MR scanner. The MagFan RT solves these challenges with a multi-component design that can be easily moved in sections that each weigh less than 12 kilograms or 27 pounds and reassembled on the patient table. Because it is a liquid-filled phantom, it is able to perform many different system checks in addition to large field of view distortion. An MR quality control protocol suitable for radiation therapy planning has all of the requirements that a diagnostic quality control protocol has, plus much heavier emphasis on issues related to absolute geometry. The MagFan RT and S162 phantoms perform a diverse set of MR system checks and particularly excel at tests that are critical to radiation therapy planning, such as distortion and laser alignment. The SMARI analysis platform provides a fully automated report of all of the measurements and performs longitudinal tracking to see developing trends. In the following slides, we'll talk about each of these measurements in more detail. We'll start the discussion with geometric distortion, which is particularly critical to radiation therapy planning. Modern MRI scanners are often reported to have distortion less than 2 millimeters. So why is it still important to measure distortion? The answer is that in order to keep distortions low, we're actually relying upon a long chain of conditions to hold. First, not all scanners have capability to give such low distortion, and so the hardware and software must be of a certain type. Next, the distortion also depends upon scanner configuration settings, such as having distortion correction turned on, as well as image protocol parameters such as the receive bandwidth. Furthermore, distortion is low only when the relevant subsystems in the scanner are functioning correctly. There are many possible failure mechanisms, such as magnetic impurities in the bore or component failures. Configuration settings and pulse sequence parameters also play a role and can give the user an opportunity to inadvertently compromise distortion. Distortions are measured locally with fiducials in known locations. The MagFan RT and S162 phantoms use a 1 centimeter spherical fiducial, which is optimized to give significant subvoxel resolution. This choice of fiducial marker enables not only extreme accuracy in the location of the fiducial within an image, but also supports use of a wide variety of pulse sequences of varying resolution, contrast, and signal to noise, enabling distortion to be measured on actual clinical sequences rather than on a limited predefined set. The local distortion is given by the displacement of the apparent position of the fiducial marker from its known location. From a set of discrete local measurements, the distortion can be interpolated to infer a continuous distortion field. The distortion, as well as all other measurements in the phantom, is measured with the fully automated analysis platform MRI. The report is organized in sections, giving pass-fail results for each section, as well as details for the expert and numerical output for longitudinal tracking. This screenshot is from part of the distortion measurement output, in which a plot of distortion magnitude versus radius from isocenter is shown. Such a plot can be used to give a quick answer to the maximum distortion at any radius. For quantitative pass-fail tests and for longitudinal tracking, numerical output is provided in the form of distortion statistics over various volumes. Shown here are statistics over two user-defined volumes. The first data column is the maximum distortion magnitude, which gives the magnitude of the worst-case distortion over the described volume. As a slightly more broad characterization of the high-end distortions, the mean of the top 10% most distorted measurements is also shown in the next column. The following 6 columns break each of these two measurements down by direction, rather than characterizing the magnitude only of the distortion. The MRI analysis provides layers of output suitable for different types of users. At the top level is basic pass-fail information for those who simply want to know if any failures were detected. At the opposite end of the spectrum, detailed information is available for those who want it. This distortion plot is an example of that and is a way to get a visualization of the spatial pattern of the distortion. Distortion is a complicated quantity to depict because the distortion itself is a vector, and the location at which the distortion was measured is also a vector. Thus, there are 9 quantities to convey. This 3x3 set of graphs shows the spatial dependence of the distortion. It is not an output that we expect to be used on a daily or weekly basis, but rather is intended for the sophisticated user who wants to understand the spatial pattern of the distortion. I want to take a slight digression here to make a general point about MRI quality control. There are 2 facets to the problem. The first is simply testing to make sure that the scanner hardware, software, and firmware is functioning correctly. For these tests, the scanner simply needs to be probed in various ways, and it's not important to replicate clinical conditions exactly, such as with actual clinical sequences. The second facet to the problem, though, is to probe for errors that can arise due to anything under the user's control, such as scanner configuration and pulse sequence parameters. To probe for these types of failures, the test should mimic clinical conditions as closely as possible, using the same pulse sequences and the same RF coils. Many failures can be caused by users not having parameters set up ideally. In addition, different failure modes in a scanner can have different effects on different pulse sequences. With the MagFan RT and S162 phantoms, quality control is performed using the same imaging protocols that are used clinically to image patients, thereby picking up many of these types of user-induced errors. As an example of such a configuration error, let's have a look at distortion correction for 2-dimensional versus 3-dimensional pulse sequences. In both cases, we're talking about full volumetric imaging sequences, but they differ in how the data is acquired. In 2-dimensional pulse sequences, the data is acquired one slice at a time. A single slice is excited, data is acquired, and then a different slice is excited and acquired. This process is repeated many times until all of the data in each slice is acquired. In a 3-dimensional pulse sequence, the entire volume of imaging is excited with every repetition, and the spatial information in the slice direction is encoded with an additional phase encoding gradient. The difference in distortion between these 2 types of sequences can be profoundly dependent upon the configuration settings in a scanner. In 3-dimensional sequences, the vendor's distortion correction is always turned on. In a 2-dimensional sequence, however, this is not necessarily the case, as there are reasons not to have it turned on related to the nature of interpolation between slices. Consequently, this choice is often a configuration parameter, and if the distortion correction in the slice direction is not turned on, the distortion can go from being in the millimeter range to the centimeter range. This example highlights the importance of testing actual clinical pulse sequences being used under the conditions that mimic clinical conditions as closely as possible. Next, we'll talk about signal-to-noise ratio, which can be an important test for detecting failures in the RF chain. Degradation of the signal-to-noise ratio is a direct image quality problem on its own, but the test is also a sensitive way to detect degradation of the radio frequency coils. Longitudinal tracking of the signal-to-noise ratio can give an early warning sign of some of the most common component failures in an MR scanner. The signal is sampled at various locations within the background fluid of the phantom, which appears bright in the image. The noise is taken from several cylindrical noise regions where there is no signal-bearing fluid. This test may detect coil degradation before it becomes a highly noticeable image quality problem. Next, we'll talk about a very important test of laser alignment. The MRI coordinate system is established by the gradient coil and the center frequency of the scanner. This coordinate system must be detected externally so that the images may be lined up correctly with the therapeutic systems. This alignment is performed with a laser alignment system built into the MR scanner, and so it is critical that this alignment system be operating correctly. The MR coordinate system can potentially be offset by hardware malfunctions or with external field disturbances. The phantoms are equipped with precise alignment markings that enable the user to position the phantom at isocenter. The summary analysis outputs both the residual translational offset relative to isocenter and the rotational offset, letting the user know exactly where the phantom ended up and how it was oriented within the MR coordinate system. In combined MR therapy systems, the test can be used to ensure that some of the large moving parts in the system, such as a rotating gantry, do not influence the MR coordinate system. Next, we'll talk about resolution measurements. Resolution measurements are often performed with intersecting dot patterns, relying on the user to make a subjective judgment of resolution. This approach has several shortcomings in addition to requiring the user to perform the test manually. It is subjective and gives a limited set of resolution values. The MagFan-RT and S162 phantoms use a sophisticated approach based on imaging a known aperture. The finite resolution of the scanner causes blurring and pixelization of the image, which could be calculated if the point spread function were known. The calculation is performed by starting with a candidate point spread function, convolving it with the pure aperture image. The resulting image is compared with the actual MR image of the aperture, and the point spread function varied until a best match is obtained. The outputs are highly quantitative and detailed, giving the fundamental resolution response functions of the scanner, the modulation transfer function, the point spread function, and the edge spread function. These functions are all different ways to look at the same information, but have their role in understanding resolution. Perhaps the most appropriate measure of resolution is the edge spread function, which tells you what the image of an ideal step edge would actually look like. The characteristic 10 to 90% transition width of this edge is a highly pertinent measure of resolution that can be used to qualify a pulse sequence or to track performance. Next, we'll talk about slice thickness measurements. The slice thickness measurement is a conventional measurement based on crossed ramp features. The features have been optimized for the thinner slices often used in radiation therapy. The automated measurements allow for a more reliable and consistent measurement than would normally be done manually. Next, we'll talk about image uniformity tests. Signal uniformity is another way to detect failures in the RF coil system, but can also be used to test intensity correction software. Uniformity is normally measured in just a single plane, or if one wants 3D measurements, with a dedicated phantom that does nothing else. The MagFan-RT and S162 phantoms provide full three-dimensional uniformity measurements on clinical sequences by sampling the background fluid at hundreds of known locations throughout the phantom. We call these locations virtual spheres because they are not actual features, but simply known areas of background fluid that are far enough away from any features to give a good sample of the local signal intensity. Phased array failures are the most common failure in an MR scanner, and these tests can detect errors that are often not caught by other tests such as signal to noise. Two primary quantities are measured: the standard deviation of the signal over a spherical volume divided by the mean of the signal. This is referred to as the normalized standard deviation. Next is the normalized spread, which is defined as the average of the 10% brightest voxels in a volume minus the average of the 10% dimmest voxels in the same volume. This test is more sensitive to the extremes of the signal and hence can better detect the local disturbances in the signal associated with a failure in a phased array coil element. In summary, MR quality control has two facets: scanner function and scanner and sequence configuration. The MagFan-RT provides, in a single scan of just one phantom, an extensive evaluation of the scanner performance that includes full 3D distortion and uniformity measurements, quantitative resolution measurements, signal to noise, slice thickness, and laser alignment. The fully automated summary analysis allows quantitative testing against user-specified limits and longitudinal tracking.